Okay, welcome to a quick recap / how-to guide on the exponential probability density function. The video link will appear here right after I've recorded it because lol, it doesn't have a link yet. Cool. Okay, so the exponential probability density function is really an extension of some of the probability work you've done in methods, and just like the probability work that you've already done, it hinges on the area under a curve. Now in this case, the curve that we're looking at is exponential, and that means that when we're looking at the area between parts of this, or the probability of something on a curve like this, it means that we're looking for areas such as this, between, for instance, these 2 points, A and B. In the case of this curve that I've just drawn here, it would follow that the area is equal to the probability that x will fall between these two values. So this is nothing new. This is exactly what we've seen in methods. You would have seen it last year in specialist mathematics when we did that statistical work as well. Now, because we're dealing with area, that means that I can express this as an integral between those 2 points. And then the last part of this would just be what our function looks like. Now, in this particular case for this function, we're just going to give it the general form of an exponential function. So I might say that f of t equals some kind of constant. Often you'll see lambda used, but it could be anything, multiplied by e of negative that exact same constant, the power of t. Now we use t here, not because it's time, but just because really we don't want to get confused between using a little x here as a variable and then also using the big X as our probability over here. So to avoid that confusion, we just use t. It's just any other variable. Similar to that, lambda is just any old constant. Cool bananas. Now, just like the area under any of the other curves that you might have seen, the total area is always going to be equal to 1. So that's nothing new for us. Now that we've actually got this function here, f of t, that means I can plug it into my area formula up here, and that means that when I'm dealing with probabilities, I'm going to be dealing with the integral, the area between a and b of my function with respect to t. And this is what we are going to be working with. Groovy. Now there is something to note here, that if t gets below 0, then that would put us over on this section of the curve over here. Now we can't be on that section of the curve, so what that means is when we're actually talking about what this function looks like, you're always going to see it noted like this. You're always going to see it written as a function of t. I've done a really bad curly whirly, such that it's exponential when t is greater than or equal to 0, and such that it equals 0 if t is less than 0. This is mostly just a formality here. You'll see this notation, but the vast majority of the work that we're going to do is dealing with finding probabilities, so that would mean using just this first one here. Cool bananas. Often in these problems, just like when you're usually dealing with probability problems, we're going to need to know something about the mean, the average of whatever data set it is that we're looking at. There is a relationship between the mean, which we are always going to denote with mu, you should be familiar with this, and that lambda constant. And that relationship is that lambda is equal to 1 on mu. It therefore follows that mu is equal to 1 on lambda. This doesn't appear in our formula book, but this is going to be really, really important to keep in our brains because this will help us with questions. So this allows us to convert between a mean to something we can actually plug into our expression and then integrate. The last thing to note when we're dealing with exponential probability curves is that if we are looking at the probability of just one point, it's always going to equal 0. So we're never ever going to look at the probability of a single event occurring. We're always going to look at the probability of it occurring between two values. Why does it always equal 0? Because that would imply that that interval on our integral is, I guess, like there's no interval. It would be between the same 2 points, and so the area under that curve would equal nothing. Yeehaw. Let's get into it. We're going to do a worked example from a textbook. That's the Year 12 text, Chapter 6.4, worked example 9. Let's have a look. So, this particular problem is dealing with random variable x, and it represents the time before the next bus arrives. If x is exponentially distributed, and it tells us that the bus arrives every 8 minutes. So it arrives every 8 minutes. If you didn't fast forward that, you're absolutely crazy. The first thing that it asks us to do is it asks us to determine the mean, it asks us to determine lambda, and it asks us to determine the probability density function. I've got all the information in this question that I need to do this. So it tells me that a bus arrives, I should say on average, lol. And that's a big giveaway that gives us our average mu. Now, because we've got mu, that means we can find lambda, because you would recall, and you have to recall, because it's not in our formula book, that lambda equals 1 on mu. So lambda equals 1 on 8. That means we can now work out our probability density function, and it's going to look like this. It's going to look like 1 on 8 times e to the negative 1 on 8t when t is greater than or equal to 0, and it's going to equal 0 when t is less than 0. Done. Found my average, found lambda, and I've got my function now as well. Now I can move on to doing something with this function. Question B asks us to determine the probability that the next bus will arrive within 3 minutes. When I think about this, I'm going to come back to our original sketch when we're looking at what the area looks like here. And we note that the area is equal to the probability between 2 points of this particular curve. So if I'm looking at the probability that the next bus arrives within the next 3 minutes, that would mean that my probability is looking at when the bus is arriving being between 0 and 3 minutes. This I can then plug straight into my probability density function. It's going to be the area here between those 2 points with respect to t. This is really, really easy for me to calculate, and 9 times out of 10 these problems will be on your ones like this will definitely be in your tech active. I get an answer of 0.313. So that's the probability of a bus arriving within the next 3 minutes in this case. Now the next thing that we might do is we might be interested in the probability that the bus will arrive, that it won't arrive within a particular amount of time. So this first example in B, we just looked at, well, what's the chance of it arriving between 2 values, nice and simple. But here we're going to determine the probability that the bus won't arrive within 15 minutes. So when I think about this, I'm thinking about the probability that it'll take longer than 15 minutes for this bus to arrive. Now this has to be infinite on the upper end because I don't know how long it's going to take for this bus to get here. It could be literally any amount of time. When I do that, I can still put together my nice little integral, but now I've got this problem of having this infinite value here. If you're a silly bugger, you might substitute a really, really large number in here. Sometimes people will do that, and you'll get an approximately correct answer, but you shouldn't do that. There's a much, much easier way. Instead of substituting a really, really large number and hoping that you get it right, we are just going to use and keep in mind that we can look at the complementary event here. Because I know, if I think about my curve, that if I was interested in the probability of it going from here all the way up here, I could calculate that by again using that infinity, or I could think about the fact that the total probability underneath this entire curve is equal to 1. And so that would mean that this probability here in pink is going to be my area before that subtracted from 1. So I'm going to use my complementary event to really quickly and easily calculate this. This would be equivalent to 1 minus the complement, which instead of from 15 to infinity would be from 0 to 15. This is again really, really easy for me to calculate, and I get a probability of 0.153. Yeehaw, nice and easy, no worries. The next example that we're going to look at is, what if we want to go backwards? So when I say backwards, I mean, what if we already know a particular probability and we want to find out the thing related to that? So I'm going to look at worked example 11. It says a particular brand of battery lasts 8 years on average. I'm first of all being asked to determine the probability that the battery will last longer than 8 years. So the probability that x is between 8 and infinity. That's the first thing I'm being asked. In order to do this, I'm going to first of all need to determine my function. I can see fairly clearly that my average is equal to 8. That means that lambda is going to be equal to 1 on 8. And so now I've got my function. One on 8 e to the negative 1 on 8t when t is greater than or equal to 0, and 0 when t is less than 0. Again, a bit of a formality, but the key thing here is really this function. That's the most important part. So now that I've got my function, I'm ready to work out my probability. Now again, I'm dealing with a probability that goes up to infinity, so a nicer way to deal with this might actually be to do the complementary event. Which instead of from 8 up would be from 0 to 8. That's going to look like 1 take 0 to 8 of my function. Again, I'm going to put this into my calculator and I get a nice easy 0.368. Lovely. Now the next part here, part B, is where we're looking at going backwards. So part B states that we want to find the smallest value of x such that 70% of batteries last longer than x years. So I'm going to think about what this particular problem is asking. It's asking me, or it's telling me, that the probability that my battery is going to last longer than x years is 70%. So I'd be dealing with x as my minimum, infinity as my max, and then that exact same function that I've been dealing with here. Now, as soon as I look at a problem like this, I'm straight away thinking, yep, sweet, I'm dealing with the complementary event here. Now, that's really easy for me to work out. If the probability of this event is 0.7, then I know that the probability of my complement is going to be 0.3, because it's going to be 1 minus 0.7. And that's going to be equal to from 0 up to x of my function. This is suddenly looking like something I can solve and find x, which is exactly what the problem is asking me to do, work my way backwards. So from here, I'm going to start integrating because I can definitely do that. I can see that 0.3 is going to be equal to, now I'm going to divide by my new power, divide by the power, so I'm going to change, so I'm going to have negative e to the negative 1 on 8t. And I care about that between 0 and x. Always good practice to make sure that you do actually show full working here, because you're going to end up with e to the 0, which we know is 1. So if you tried to skip this, you might have ended up with a bit of a silly. So negative 1 take 1 is going to be plus. I'm going to shift that over. Negative 0.7 equals negative e to the negative x on 8. I'm going to divide both sides by that negative 1 and cancel that out. So I get 0.7 equals e to the x on 8. I'm going to ln both sides. And I get negative 8 times ln of 0.7 equals x. I put that into my calculator and I get x equals 2.9. So this means that 70% of batteries last for at least 2.9 years. Nice and easy, done. Now for a you-do, from the EAs we've got we've got a few really good choices, but the ones I'm going to go through right now, I'm going to have a look at 2024 paper 2 question 9, and then I'm going to have a look at 2024 paper 1 question 18. Groovy. Let's have a squiz. So I'm going to start with 2024 with paper 2. Lol. Cool. Okay. Paper 2 question 9, here we go. So it says a random variable x has an exponential distribution with a probability density function given here to us. It says that given that the probability that a particular value is between 0 and k is equal to 0.5, we want to determine k. So here we're actually going to be working backwards. So let's have a look. Now this is saying that it's saying that the probability that it falls between 0 and k is equal to 0.5. So that would mean that I'm dealing with 0 up to k, and that function, if I remind myself very, very quickly, is 1 on 5. Cool. So straight away I can see that I'm going to solve for k. So this problem now means that 0.5 is going to be equal to, and I'm going to integrate this, so I'm going to divide by that power, so I get negative e to the negative 1 on 5 t between 0 and k. You'll notice that these integrals always end up pretty much exactly the same. So 0.5 is going to be equal to negative e to the negative k on 5 once I sub that in for t, minus negative e to the 0. So 0.5 equals negative e to the negative k on 5 plus 1. Negative 0.5 equals negative e to the negative k on 5. This is on the Tech Active paper. Keep in mind I'm going to ln both sides now. So I get negative 5 ln of 0.5 equals k. And when I put that into my calculator, I get an answer that is right around 3.47. So the correct answer here is going to be D. The next one that I'm going to have a look at is question 18 from paper 1 in 2024. So, when I have a look at this problem, that's the wrong one. Oh my goodness. Here we go, we're here now. Okay, question 18, 6 marks. A random variable x has a probability density function given by this value below. It asks us to determine the value of k. Now notice a few things here. So first of all, you'll notice that we're dealing with an arcsine function in here. So this is a little bit different. It's not an exponential probability density function, it's just a probability density function. But I'm going to follow these same steps. Question 18 is the second last question on this paper. So it is a complex unfamiliar. Now I'm asked to determine the value of k. Let's dive in and have a look. The first thing that I'm going to do here is I'm going to use one of those earlier properties, which was that if I think about the area underneath the entire curve, I know that that equals 1. So straight away I can set myself up for success here by noting that the total area 1 is going to be equal to the entire range of my function, and this function gives that to me because x is going to be between 0 and 1. So that means I can set this up really nicely and say that my probability of 1 is going to be equal to the entire length of the entire area underneath my function of my function. Groovy. So now when I look at this, I'm just going to do an integral, and I've got some values to sub in, so I'm going to be able to solve for k. So my first step, I'm going to pull k out the front because it's a constant, and I'm left with this integral of arcsine of x dx. Now note that we're on paper 1 here, so we don't have access to a calculator. I'm looking at this and straight away I'm thinking, okay, what were some of the integration techniques that I've got? Now if I check my formula book, I would see really quickly that I don't have any kind of integral that deals with arcsine. I've got derivatives of arcsine, but I don't have integrals of arcsine. This is your big hint that, okay, we don't know how to integrate this, but I do know how to derive it, so that big hint is telling me I'm going to use integration by parts. So I'm going to set this up, and keep in mind that you've got this formula in your formula book. Integration by parts says that the integral of uv dash equals uv minus the integral of vu dash. I've just got to choose my u and my v dash. Your u, you want to choose to be something that's really easy to derive, and v dash, you want to choose to be something that's really easy to integrate. This is one of those trick ones where it looks like we've only got one function, but we've really got two because there's an imaginary little 1 out the front here. So straight away, I can see now that the 1 is going to be really easy to integrate. So I'm going to set that to be v dash, which means that v would be x. And then u dash I'm going to set to be arcsine of x. And this is super easy to derive because this is actually one of the derivatives that appears in our formula book. So the derivative of arcsine of x on a is this expression every single time. We're not really dividing ours by anything, so a is going to be 1 in our case. So that means my integral is going to look like 1 on the square root of 1 squared minus x squared. You would remember a really similar problem, which was a complex unfamiliar in our IA3 exam. It was the integral of arcsine squared. Alright, anyway, now I'm going to plug these values in, and now I'm actually dealing with k times the integral of u times v, which is x times arcsine of x, minus the integral of v, which is x multiplied by 1 on the square root of 1 squared is just 1, take x squared dot dx. Cool. Now be careful here because this might look like you've got to integrate by parts again, but you don't. It might look like you have to do partial fractions because this thing on the bottom, but you don't. For a case like this, I'm actually just going to use a really simple substitution. I'm going to let u equal 1 take x squared, and I know that this substitution is going to work because du dx equals negative 2x. So that's going to enable me to cancel this x out the front. When I rearrange, I get dx equals du on negative 2 of x. So now my expression looks like this. X dot 1 on square root of u dot du on negative 2x. Straight away I can see that this x and this x cancel. Should probably make that look like a dot. That 2 I can bring all the way out the front if I'd like to. So I'm dealing with, if I bring that negative 2 out the front, it's going to be a plus 2 dot the integral of 1 on root u du. Don't overcomplicate this. This is a very, very simple problem. We're not going to use ln or anything crazy. We're just going to express it like this. So u to the negative half. If I integrate this, I'm going to add 1 to the power and divide by the new power. Oh, and I just realized that should be a 1 and 2 at the front. Now when I divide by a half, it's really equivalent of multiplying by 2. And now if I want to, I can sub u back in. I'm actually going to write my whole expression out now. K times x multiplied by arcsine of x plus 1 on 2, 2. Now u, I said, was actually equal to 1 take x squared. And I've just changed my power back. These two cancel. Okay, so now I get 1 on k equals, oh, I don't have to do it like that yet. Nah, I'm gonna keep it like this. 1 equals k times x arcsine x plus the square root of 1 take x squared. Now at this point it's really easy to get lost in what the hell you were doing. We were finding the integral between 0 and 1. So now that I've actually found the integral, I need to remember to actually find the definite integral here. So that's going to look like subbing in 1, which would be 1 times arcsine of 1 plus square root of 1 take 1 squared. All of that needs to be subtracted from 0 times arcsine of 0 plus square root of 1 take 0 squared. Lovely. Arcsine of 1 is really quite easy for us to calculate. I'm just going to think about what does my sine curve look like, and we know that it looks like this. Oopsie. And now I'm thinking, okay, well, when does sine equal 1? It equals 1 right here at pi on 2. So that means that arcsine of 1 equals pi on 2. So I can sub that in now. So 1 times pi on 2 plus 1 minus 1. Oh, sorry, no, I've done a mischief, There we go, that looks better. This isn't 1, this is equal to 0, lol. Take 0 plus 1. Here we go. Alright, now we're cooking. So 1, now when I do simplify this here, I've got k times pi on 2 take 1. I'm going to divide both sides by pi on 2 take 1, and I get k equals 1 on pi on 2 take 1. And I'm done. I've found my value for k. You'll notice that in these solutions, they sort of go one step further and they multiply, they I guess, rationalize this, so everything's multiplied by 2, just to get rid of that pi on 2 on the denominator. I don't think you'd lose any marks if you didn't do this. So this is a nice application of probability density function work with our integration techniques as well, which is pretty good. And then that's pretty much all the tools that you'll need in order to tackle exponential probability density function questions.